Okay, today we will have a presentation on op amp circuits and signal conditioning for microsystems devices. So, we will actually continue from where we left in our previous discussion on the amplifier little bit. So, today we will go through that portion of amplifier, then op amp concepts, basic op amp circuits and signal conditioning circuits. So, we saw last time, I just had quickly gone through this portion of common base BJT, common base amplifier circuit. Here what I would like to point out is there is DC as well as AC. The DC VE is applied, is connected to the emitter lead through a resistance RE, so that the emitter current is fixed by this loop equal to VE divided by RE approximately. Strictly speaking, it is VE minus VEB divided by RE, but VE will be large compared to VEB, because VEB is of the order of 0.65 volts. So, IE is fixed once I fix VE and RE, that is the biasing. Once I fix IE, if the collector base is reverse biased, whatever IE flows through emitter will reach the collector. So, DC current IE, if it is 1 milliampere, collector current IC will be 1 milliampere DC. Now, what we are talking of is, so this DC bias VE and VC are applied so that the transistor is operating in the active region, so that emitter base junction is forward biased, pumping a current of I DC equal to 1 milliampere or whatever you want, set by this voltage and the resistance, and correspondingly the collector current is equal to, if it is 1 milliampere, that is also 1 milliampere. Now, if R is equal to 1 kilo ohm, if 1 milliampere flows through the circuit, the drop is 1 volt. So, if this is 4 volt, the voltage BBC will be actually 4 volts minus 1 volt, 3 volts. So, there will be a reverse bias of 3 volts. Suppose the current is 2 milliamperes, then the drop will be 2 volts. So, 4 volts minus 2 volts will be reverse bias. Okay. Now, what we do is, if to use it as an amplifier for small signal purposes, I apply voltage VE, small VE in series with this is not the way it is applied, but I am showing it schematically like this. So, VE sets in a current IE, small IE, which is AC current, and that small IE, okay, when it flows, develops a voltage V in, that is AC voltage across the emitter and the base. Now, how much voltage flows through that depends upon how much current you pump in. Okay. If I pump in some small signal current IE, okay, the drop V in will be equal to IE into RE, where RE is the junction resistance of this forward bias diode. It is actually incremental resistance or small signal resistance, that we will see how to find out. This RE will actually be small. So, input voltage V in will be equal to IE into RE. Okay. Now, output current IE, small IC will be almost same as IE, actually it will be alpha times IE, alpha is the current gain. So, if this IE will be much smaller compared to the DC current, if DC current is 1 milliampere, this may be microamperes of that range. So, IC also will be same, okay, or at the most if it is 1 milliampere, this may be 1/4 of a milliampere, collector current also be 1/4 of a milliamperes. So, now IE is this, small IE is the AC current, small IC will be the AC collector current, which will be same as the small IE. So, this will result in a AC voltage drop across the RL. So, voltage drop, AC voltage drop across RL will be IC times RL. AC voltage input V in is equal to small IE into RE, and IC by IE is alpha. So, therefore, the voltage gain V naught divided by V in here will be equal to alpha times R L divided by R E. Now, what is R E? We have said R L, let it be 1 K, 1 kilo ohm centimeter, kilo ohms. Now, R E is actually the incremental resistance of this forward bias junction, which is actually delta VEB divided by delta E, or delta VEB is small signal voltage, that is V in, delta I is small signal current, that is I E. Okay. Now, how much will this be? You find out like this. DC current I E is I naught e to the power of V E by V T. Delta I E by delta V E B will be equal to 1 by V T into I naught e to the power of V E by V T. That is, delta I E by delta V E B will be I E by V T. Therefore, and what is V T? V T is actually K T by Q. K is the Boltzmann constant, T is the temperature in degree Kelvin, Q is electronic charge. At room temperature, this turns out to be about 25.8 millivolts. I put it at 25 millivolt for simplicity at 300 degree Kelvin. So, R E is V T by I E, okay, because delta I E by delta V B is I E by V T, delta V B by delta I E as we seen here is R E, V T by I E. Supposing the voltage is 25 millivolts, V T is 25 millivolts as calculated here. If DC current is 1 milliampere, R E is 25 millivolts by 1 milliampere, that is 25 ohms. So, if you have 1 milliampere DC current flowing through the collector, incremental resistance is actually 25 ohms, because DC current also is 1 milliampere. So, that is 25 ohms. So, the voltage gain now will be R L by R E, that is 1 kilo ohm divided by 25 ohms, that is 1, okay, that is 40. So, you will get a gain of 40 if the DC current is set at 1 milliampere. Suppose the DC current is 2 milliampere, what happens? If the DC current is 2 milliamperes, the DC drop across this increases back to 2 volts. So, if this are 4 volts, the voltage across this will be 2 volts DC. But this ensures that even though this is reduced from 3 volts to 2 volts, this junction is reverse biased. So, transistor is still in the active region. So, I C will be equal to I E practically, and small I C will be equal to small I E. Therefore, the same equation holds good in this case. Only difference is, since the current is now 2 milliampere DC, okay, your R E will be 25 divided by 2 milliampere, that is 12.5 ohms, which would make the voltage gain is equal to 1000 divided by 12.5, that is 80. Okay. So, that means what you say is, if I choose larger and larger I E, the gain will go up because R E keeps on reducing, but there is an upper limit on this. Okay, let us see how much is that. So, can I go on increasing the I E? See here, this is the output characteristics of the transistor. All for each I E 1 milliampere, collector current is 1 milliampere, and so long as the reverse bias is present, current is constant 1, 2, 3, 4. These are output characteristics which you saw. Now, the current is also decided by, when I apply voltage 4 volts, the voltage VBC will depend upon how much is the current and how much is the resistance. That is related by VC is equal to IC times RL plus VBC. So, you can see this is equation of a straight line IC versus VC if I plot. So, you can see when IC is equal to 0, VC is equal to VBC. VBC is on the x axis, that is equal to VC, 4 volts. When VBC is equal to 0, if I keep on increasing the current, 4 volts, supposing it is 2 milliampere, 2 volts drop, 3 milliampere, 3 volt drop, 4 milliampere, 4 volts drop, applied voltage 4 volts, this will be equal to 0. So, you can see that when this is VBC is equal to 0, IC is equal to VC is equal to IC times RL, or VC is 4 volts, RL is 1 K, this is 4 milliamperes. 4 volts by 1 K is 4 milliamperes. So, what we say is, in this type of operation, I can keep on increasing this particular current through this transistor in order to get better and better gain, because it is V t by I e. I can keep on increasing till the current is 4 milliamperes, emitter current is 4 milliamperes. Once it becomes 4 milliamperes, VBC becomes equal to 0. If I go beyond that point, the collector base junction will get forward biased. So, once it gets forward biased, collector current will not increase proportional to emitter current. So, IC will saturate at that 4 milliamperes. So, therefore, there is no point in increasing the current beyond 4 milliamperes. Okay. So, when it is 4 milliamperes, the output voltage peak will be actually equal to 1 k into 4 milliamperes, 4 volts. So, that will be maximum swing of this output voltage will be will come down to 4 volts. Now, on the other side, if IC equal to 0, that will be 4 volts. If IC equal to 0, there is no collector current, DC current at all. If there is no DC current, the output voltage will be clamped down to this VBC itself, it will not change beyond that point. So, therefore, you will have clipping between 2 volts peak and 0 volt on the other side. So, the swing can be between from 2 to 4 and 2 to 0, 4 volts maximum peak to peak you will get in this device. So, that is what I am trying to point out is the sinusoidal operation of the signal will stop when the amplitude of the sinusoidal signal reaches close to the supply voltage, or when the amplitude reaches close to that 0 voltage point. If there are two supplies VB on the both ends of the amplifier, then you will have plus and minus upper limits. In this case, you have got plus and 0, okay? 0, 2 and 4, that is all. Okay, now let us go on to this, what I wanted to point out last time, finish up, then let us take a look at this operational amplifiers. This is a very popular device. Operational amplifier is a high gain direct coupled amplifier which operates with the differential voltage between input two input terminals. Okay. Whatever is the difference voltage gets amplified. If there is a common voltage, then the difference voltage is 0. At that point, if you apply even the voltage between the two same, output will be ideally be equal to 0. Okay. The symbol for the op amp is given like this. It has multiple stages. Input stage which provide high input resistance, so that the current drawn is minimum. We have discussed this aspect. Middle stages to provide high voltage gain. So, input stage, middle stage for high voltage gain, output stage to give low resistance. Okay. Now, let us just take a look at the op amp terminals. There are several terminals. Okay. The ideal one or the most important terminals are, I have marked it as 2, 3, 4, 6 and 7, 1, 2 etc., 1, 5 etc. are other terminals which I am not showing. Terminal 2 is inverting input. The output that results from the input at this point will be of opposite polarity. For example, if I apply plus 1, there will be minus 1 here. Terminal 3 is non-inverting input. The output that results from this has same polarity. If I apply plus 1 here, it is plus voltage here with an amplification. Okay. 4 and 6, 4 and 7 are the supply voltages. You will apply plus voltage here, plus 10 volts, minus 10 volts nominally, or plus 5 volts and minus 5 volts nominally, which supplies the power required for the op amp. Here you apply your signal. The signal in the case of op amp can be DC and AC. That is what you mean by saying direct coupled amplifier. So, output terminal is V naught is here. There is always a ground point somewhere here that I am not showing here, with respect to which you may apply the voltages and measure the voltages. This is simple. Equivalent circuit and ideal model. The output voltage V naught of the op amp is related to the open loop gain or the amplifier gain A naught, and the difference voltage V d. This is this is the inverting terminal, this is a non-inverting terminal. If you apply V plus and V minus, the difference is V plus minus V minus. Okay? You will get an output voltage across these terminals. If you do not connect, okay, you will get the output voltage, which is actually difference between the two, that V d equal to V plus minus V minus into the gain, differential gain of this amplifier, that is V naught. Now, when you use it in circuit, one has to remember that A naught is very large. This ideal equivalent of this is the amplifier. R naught, output resistance, is very small in this case, in these devices, maybe 50 to 60 ohms or even lower. Okay. R naught is, I am putting it 0 here. So, the output is a voltage source, an ideal voltage source, whose value is V naught is equal to A naught into V d. Now, A naught, if it is very large, for a finite V naught, if A naught is very large, V d will be very small. What we are telling is, you will get a finite output voltage from this amplifier with very small voltage across the two terminals. So, for all simplified calculations, one can always take this difference to be negligible. That is, there is a finite voltage, so that there is output voltage coming, but that is negligible for making simple analysis. Strictly speaking, you have to take this R input, which is very high. You have to take into account the difference between the two voltages here, but as you see, it simplifies very much in all the op amp circuits. Okay. So, model for the ideal op amp is input resistance is infinite, output resistance is 0, ideal voltage source, A naught, the gain V naught divided by this V d, that is infinite, tending to infinite. Then there is one more factor. So, A naught is actually the differential gain, which is very large. Now, the common mode gain, supposing I apply same voltage to these two terminals, V plus and V minus I short, and apply voltage, ideally you must get 0 voltage. In practice, you will have some small voltage. So, that if I say AC, VC is the common voltage, I will get an output voltage V naught C. So, V naught C by VC is the common mode gain. A naught is the differential gain. A naught divided by common mode gain, AC, is the common mode rejection ratio, which has got to be very large, 1000 or very high, 1000 or even more, ideally infinite. A naught is the differential gain, AC is the common mode gain. Okay. So, if that is the thing, whatever, supposing there is 0.5 volts difference in the voltage, and there is a noise signal of 0.1 volt here and 0.1 volt here, which is common, that noise signal will not be amplified, only the difference signal will be amplified. This is the greatest merit of the op amp amplifier, that is, whatever background signal is present is eliminated, because the common mode gain is ideally 0 or very small. In practice, the op amp with MOSFET, when you use MOSFET amplifiers inside this, they have RI of 10 to the power 12 ohms, which is very high. See, even if you have 1 volt input, it is 10 to the power minus 12 amperes, which is picoamperes. Okay. So, with that understanding, we will proceed. We take this voltage negligible and gain as infinite. Now, the op amp transfer characteristic V naught versus V d. V naught versus V d, ideally if A naught is infinite, this will go vertically up there, but there is a finite slope which is very steep, telling you that A naught is very high. And as I pointed out in the case of amplifier, when the output voltage approaches that of the supply voltage V s plus, it will no longer increase beyond that. If ideally, when this becomes equal to V s plus, it stops increasing. That is the saturation point, as in the case of the amplifier that I pointed out. Since there are two supplies, V s plus and V minus, you will have two saturation points at V s plus and V s minus. But in practice, it will not go up to V s plus, it will be less by about a volt, because there are other drops which are present within the op amp itself. Okay. So, as a result, you can apply the signal voltage between which will be useful across the two terminal V plus and V minus will be just about 20 to 30 millivolts at the most here. By the time it will go to infinite. Okay. So, this will be the slope into A naught will be the output voltage. Okay, that is the transfer characteristics, and we will see now what one has to guarantee is that the differential voltage appearing across the two terminals here is very, very small. That is done, taken care of very precisely in all the op-amp circuits with the connect external resistors. Entire gain, this is the open loop gain that you are talking of, A naught, nothing is connected, very difficult to control. We have a small delta V here, it will take the transistor into the saturation, op-amp into saturation. So, one of the very useful applications is a finite gain inverting amplifier. What is meaning of inverting amplifier? If I have plus voltage here at the input, you get minus output, and it is amplifying. So, the output V naught will be more than Vs signal. So, you can see the simplified analysis taking the ideal op amp is the non-inverting terminal is connected to ground. That means, the potential here is 0. As we already pointed out, you assume that in the ideal case the difference between the two terminals is very, very small. So, we neglect that compared to the other voltages. So, if that is neglected, the potential here at this inverting terminal is also 0. If that is 0, so we make all through this assumption simplified. More involved discussions you can make, you will arrive at back into the same conclusion when the A naught is very large. Okay? This is assumption. Input current is 0, input voltage is 0, input resistance is high, therefore, input current is 0. So, all the current path is from Vs through this resistor to this output. So, I 1 is equal to I 2. What is the current I 1? I 1 is equal to Vs minus Va. Va is 0 because this is 0. Vs minus Va divided by R 1, that is Vs divided by R 1 is I 1 on the left hand side here, and that is equal to this current here. That current is 0 minus V naught divided by R 2. 0 minus V naught is minus V naught divided by R 2 is the current in the direction. So, equating the two, Vs by R 1 is equal to V naught by R 2 minus. Therefore, V naught is equal to Vs into R 2 by R 1 minus. So, the gain of this amplifier is actually negative, and the output is negative, and the gain is magnitude is R 2 by R 1. I can get 0.5 volts input if I have. Here the input will be very, very small. So, if I have 0.5, if the gain is 10, I will have 5 volts output. Okay, one has to ensure that the output power supply voltage for that should be more than 5 volts. If the power supply voltage for the gain is, if the power supply voltage is 3 volts, the output voltage is saturated at 3 volts. So, you will have clipping. Okay, this is the non-inverting amplifier. Now, instead of grounding this is the inverting amplifier. Instead of grounding the non-inverting terminal, let us do one thing. Let us apply the signal to the plus terminal, which is non-inverting terminal, okay, and connect the resistor between like this, ground R 1 and R 2. If I do that, now you can see this is V of s. The assumption is that the gain is infinite, voltage difference here between the two terminals is negligible. Therefore, the voltage here is Vs, Va is equal to V of s almost. Strictly speaking, this will be slightly different because there is a difference in voltage, but for all practical purposes I can take Vs. Va is equal to V of s. Therefore, okay, the current, there is no input current here, the current flows from V naught through this to ground. That is the path for the current in the external circuit. So, what is the voltage V A? V A is equal to V of S, that is equal to V naught divided by R 1 plus R 2 into R 1, because this is a potential divider. V naught gets divided between R 2 and R 1, and this output voltage V A with respect to this ground is V naught into R 1 divided by R 1 plus R 2, and and V A is equal to V F S. So, V S is equal to R 1 divided by R 1 plus R 2. So, V naught is equal to V S into R 1 plus R 2 by R 1. In other words, V naught is 1 plus R 2 by R 1 into V of S. So, if R 2 by R 1 is equal to 2, it will be 1 plus 2, that is 3 times V of S. I will have a gain of 3 for this amplifier, and polarity will be V naught will be same as V f S. If it is plus, it is plus. In fact, this particular type of amplifier is very commonly used in Wien bridge oscillator for amplitude stabilizing purposes. Okay, or for Wien bridge oscillators, to realize the amplifier of gain 3. You have RC combination and an amplifier of gain 3, you can precisely get this gain 3 for the Wien bridge oscillator by choosing this ratio as 3. This is very commonly used. Now, other configurations of the op amp. Voltage follower. What is the meaning of that? The output is equal to input, no voltage gain. How is it obtained? Connect this output terminal to this inverting terminal. Since V s is applied to the plus terminal, voltage drop across these two is negligible. So, here also that is V of S, that is out. So, V naught is equal to V of S. V of S is here, V of S is present in this point. Okay. Therefore, V naught is equal to V of S. Voltage gain is not there. What is the use of this? All that you get is you can use it as a buffer. If I connect this to the previous stage of an amplifier, output stage of an amplifier, because this has very high input resistance, it will not draw any current. So, I can connect this in between one stage of an amplifier and next stage of signal conditioning circuit or a measuring circuit. So, that the output resistance here is small, input resistance is large, this does not load the previous circuit, and since output resistance is practically 0, entire voltage is available for the next circuit or the next measuring device. So, this is the buffer, very commonly used. Then the integrator. Instead of using a resistor in this portion, a inverting amplifier, I connect a capacitor here. We have seen that current I 1 is equal to current I 2. Now, I 1 is V s by R, I 2 will be, this will be useful only when there is a time varying signal, because current through a capacitor is C dV by dt. Only if there is voltage change, then only it can allow the current to flow. So, I 2 is equal to, this is 0, this is V naught, minus C into dV naught by dt. So, these two are equal. So, therefore, V s by R is equal to minus C into dV naught by dt, integrating V naught is equal to minus 1 by R C into that V s times dt, which means that if I have a signal input here, what I get at the output is integral of the signal. Very useful to generate sawtooth from a square wave. I have shown it here. If there is a wave shape like this square wave, for one square I have shown, integral of that is linear. So, it is a sawtooth, it will come down, so it can keep on increasing and decreasing like that. So, integrator. If I interchange the capacitor, put it here and a resistor here, that can, by the same way you can analyze and see that I 1 is C dV s by dt, because this is 0. Voltage drop across the capacitor is V of s, C dV s by dt is the I 1, and I 2 is minus V naught divided by R, because this is 0, this is V naught. V naught divided by R is current I 2, equating minus V naught by R and C dV s by dt we get V naught is equal to minus R C into dBs by dt, which means that the output will be differential of a input. In other words, if I have a square wave, if I have a sawtooth wave shape, I can differentiate it and get a square wave. Okay. Now, let us take a look at a differential amplifier using an op amp. Here, you can see that V 1 is applied to the non-inverting terminal through this resistor, and V 2 is applied through this inverting terminal to the output like that. So, what we want to find is what will be the output voltage for this case. V 1 and V 2 are applied. You can analyze this very simply by considering this circuit as superposition of these two circuits. Okay. In this portion, what I did do is, I have found out what is the voltage V b is, okay, and take that V b as the input voltage to the op amp and consider the V 2 as 0. I am considering only the effect of this V 1 to find out what is V naught with V 1 alone. Next, what we will do will be ground this point, consider the effect of V 2 alone here. If I ground this point, it is as good as grounding at this point V b. Ground this point, consider how much output I will get with V 2 alone. So, V naught will be V naught 1, which you get considering the effect of V b alone and considering V 2 as 0, what is the output, plus the effect of this circuit where V 1 is considered 0 and take the output V naught 2 with V 2 present like this. Now, let us see what it is. What is V b? V b, nothing else is coming here. V b is equal to V 1 divided by R 3 plus R 4 into R 4, R 3 plus R 4 into R 4. I have chosen I have written R 3 R 4 to distinguish between the two, but in reality R 3 is made equal to R 1 and R 4 is made equal to R 2. Therefore, V b will be V 1 into R 2 divided by R 1 plus R 2. Okay. V b will be R 2 divided by R 1 plus R 2. Okay. Now, if I have V b here applied from this is the inverting amplifier. The V naught 1 due to this inverting amplifier will be V b into 1 plus R 2 by R 1. This is what we saw just now here. If there is a signal, V naught is equal to V s into R 1 plus R 2 by R 1 or 1 plus R 2 by R 1, 1 plus R 2 by R 1. So, V naught is 1 is equal to V b into 1 plus R 2 by R 1. Okay. Now, V b is equal to, we saw if this is R 1 and it is R 2, that is equal to R 2 divided by R 1 plus R 2. So, R 2 by R 1 plus R 2 can R 2 plus R 1 plus R 2 in the numerator cancels with R 1 plus R 2 in the denominator and you get R 2 by R 1. So, for this amplifier the gain is V 1 into R 2 by R 1, that one that we have in that goes off because V b is now applied through this resistor. So, you get V naught 1 is equal to V b into 1 plus I am sorry V naught 1 is equal to V 1 into R 1, because V b is simplified now using this relation. So, V naught 1 is related to V 1 by R 2 by R 1 with other signal is not there in this amplifier. Okay. Now, V naught 2 for this case is very simple. I ground this point, find out how much is the V naught 2. This is the inverting amplifier. V naught 2 is V 2 into R 2 by R 1 with a negative sign. V naught 2 is V 2 into minus R 2 by R 1 into V 2. So, as I mentioned earlier, the total voltage output here will be this plus that is V naught is equal to V naught 1, which is V 1 into R 2 by R 1 plus V naught 2 which is minus V 2 by into R 2 by R 1. So, that is R 2 by R 1 into V 1 minus V 2. So, ultimately what we conclude is this is an amplifier which gives an output equal to the difference between the two V 1 minus V 2. If V 1 is plus connected to this plus terminal, V 2 is connected to minus terminal, the output is positive and the gain is equal to R 2 by R 1. Precisely you must have R 2 by R 1 and R 2 by R 1 here. Okay. Now, you can see that the ratios and all are controlled, the gain is controlled by these two resistors R 2 and R 1 and both of them must be having R 2 by R 1 exactly same. Okay. Now, you can modify this circuit. The benefit of this circuit of course is it will have high input resistance and output is exactly difference between the two. You can get still higher input impedance and another control additional gain by modifying the circuit, which you call it as usually instrumentation amplifier. With instrumentation amplifier you want to increase the gain further, you want to have very high input resistance. Okay. Already you have got very high input resistance there. Now, if I have two of them connected like this, between the VS1 and VS2 very large input resistance you will get, and let us see how this gain can be increased further. Notice in the previous case it is R 2 by R 1 into V 1 minus V 2. Okay. So, in this case the gain will be output voltage will be VS1 minus VS2 into R 2 by R 1 as in the previous case multiplied by a factor 2R divided by RG, that is obtained by connecting this like this. So, let us quickly, this is a simple circuit, there is no problem at all. See V 1 minus V 2, okay. If I take V 1 minus V 2, then this will turn out to be minus sign, V 1 minus V 2 into R 2 by R 1 will be V naught. How much is V 1 minus V 2 is we have to find out in terms of V S 1 and V S 2. So, here you can see here the simple this looks difficult, but very simple. This is the differential amplifier which we put in the previous slide, that is V 1 minus V 2 and that is amplified by a factor R 2 by R 1 with a negative sign. What is V 1 minus V 2 we have to find out, that is this difference, that is output voltage here minus this voltage. What is output voltage here? That is drop across R G plus drop across two resistors. Drop across R G is, what is the voltage here? Same as that V S 1, because drop across the two terminals is negligibly small in op amp. So, this is V S 1 and this minus is connected, this voltage is at V S 2, that is the difference between the two is negligible. So, this is V S 2, this is V S 1, difference is V S 1 minus V S 2, okay. That is the voltage that is present here, and across what is the current through this R G? Current through the R G is V S 1 minus V S 2 by R G. Okay. So, the total voltage V 1 minus V 2 is V S 1 minus V S 2 plus V S 1 minus V S 2 by R G into R plus R, that is 2R. 2R into V S 1 minus V S 2 by R G, 2R into the current, that is V S 1 minus V S 2 by R G, okay, plus V S 1 minus V S 2, that is the difference. That difference voltage, okay, that is this quantity I just put again here into minus the difference voltage into R 2 by R 1. So, you can see the output voltage in this case compared to previous case it was amplified only by R 2 by R 1 on the signal. Now, there is additional factor which comes up as 2 R by R G. So, I can choose this value of R G so that I can increase the gain of this amplifier. So, the differential amplifier with this arrangement is often used or as an instrumentation amplifier with very high gain because it is R2 by R1 into a factor which can be controlled by this Rg, and very high input resistance, because there are coming two inputs are coming here across between these two terminals, input of this op amp plus this quantity. So, you get very high gain, and the usefulness of this is extremely high input impedance. This is called an instrumentation amplifier. So, the difference between the instrumentation amplifier and ordinary difference amplifier is additional stage here. Extremely high input impedance, high common mode rejection ratio, that is, it is able to reject the signal that is common to both terminals, but to amplify a differential amplifier. Okay. So, it amplifies the difference in voltage with very high gain, and the common mode gain is very small, it rejects that. The high common mode rejection ratio is very useful for receiving very small signals buried in large common mode effect, offsets or noise. So, as I pointed out already, if there is noise signal coming between the two input terminals, that is not going to be amplified, because common mode gain is very small. But the difference between the voltages, which may be even small signal, that will be amplified quite a bit, because the gain is large. Okay. Now, you can also choose. See, the difference that you are opting now is, I do not want that very high gain, because if I am getting already very high gain by means of this R2 by R1, I want only a fixed gain. I can change this. In this case, I can change the gain by changing Rg, but if I remove this Rg, then use it like this. I remove the Rg, use this as a unity gain amplifier. Okay. Whatever you get here, the Vd here is Vs1 minus Vs2. How is that possible? Vs1 is same as here Vs1, Vs2 is same as Vs2 here, because of unity gain. So, Vs1 minus Vs2 is the input voltage, and from here onwards, this is the differential amplifier which gives into R2 minus by R1. There will be a negative sign coming in this particular circuit, because you put it like this. Okay, put it Vs1 minus Vs2. Since I have put Vs2 minus Vs1, there is no negative sign, because you take this as plus minus that. If I had put Vs1 minus Vs2, I would have got a negative sign here, as in the previous case. Okay. Okay, this is the another version of the instrumentation amplifier with gain not so high, but it gives very high input resistance and very high common mode rejection ratio. Okay. Now, we will come to some of the signal conditioning circuits for microsystems. One of the today we will focus only one such circuit or device, which is popularly known as analog to digital converter, or A to D converter, or ADC. Here, why do you need analog to digital conversion? The output signal of most physical systems, such as pressure sensor, acceleration sensor, etc., are analog. When you say it is analog, that means that the signal is continuously varying with time. At each instant of time, the signal is present. Okay, that is analog. You can see a sine wave is an analog signal. Now, we need to convert them into binary form to enable processing in the digital domain, and processing in the digital domain enables you to achieve higher efficiency and higher reliability, less of noise, and you can process it with great efficiency. These are some of the advantages of that digital signal processing, much more efficient than the analog, much more simple. You can have similar type of circuits to process the signal and making the integrated circuits for digital circuit is much simpler. All those advantages are there. So, today all the processing is done in the digital domain, and therefore, you require to convert the analog signal into binary form, that is ones and zeros. It is present over a certain duration with 1, certain other duration with 0. So, it is a combination of these plus minus etcetera. Okay. So, analog ADC or analog to digital converter is a circuit which performs this conversion as the name itself indicates. Now, in this type of ADC, in the ADC circuit, the input voltage is sampled at regular intervals T of s, and the output is digital in binary form. Okay. It is sampled, for example, if there is a sine wave, you take that particular signal at T 1 and convert it into digital form, then take it at T 2 after interval T of s, convert that into digital form, and the entire output of the ADC is a sequence of binary numbers. Okay. So, the input output scheme of a n bit ADC. Okay. Now, for example, what is the meaning of n bit? If there are 3 pulses to decide one word, then it is called 3 bit. For example, I can write a number, a voltage 0 as 0 0 0. Okay. There are 3 bits are used, each one is a 1 pulse. Here there are all the pulses are 0. Second one, if you take 0 0 1, pulse is 0, pulse is 0, third pulse is 1. Okay. That is high, the pulse is present here. Now, in a digital form 0 0 1 is 1. So, it may represent 1 volt. 0 1 0 in a digital form is 2. 0 1 1 is, I am sure you have studied this in some place or other. So, I am just saying that, see, this is the n bit, 3 binary numbers are used here, 3 bits are used to realize the number. The first digit is each case you multiply it by 2 to the power of something. Here it is 1 into 2 to the power of 0, that is 1. Here this is 1, this is 0 into 2 to the power of 0, that is 0. 1 is 1 into 2 to the power of 1, that is 2, that is why this number is 2. Here this is 1 into 2 to the power of 0, that is 1. This middle number is 1 into 2 to the power of 1, that is 2, 2 plus 1 is 3. So, here 1 into 2 to the power of 2, that is 4, 0 into 2 to the power of 0, this multiplying weighting factor is 0 0, this is 4. So, this is 4, this you see this is 1 into 2 to the power of 0, this is 1. So, 4 plus 1 5. So, these numbers indicate 0, 1, 2, 3, 4, 5, 6, okay, then 7. Now, the analog ADC has analog reference voltages V reference, against which the analog input voltage is compared. You compare the input voltage against this reference. Okay. Digital output word tells us what fraction of V reference the input voltage is. Okay. A 3 bit, to understand it, a 3 bit ADC analog digital converter, number of bits n is equal to 3. For example, here number of bits is 3. It is a 3 bit ADC, where n, if it is a n bit, number of bits is n. For example, if it is 4 bits, there will be 4 numbers here, that is n is equal to 4. Now, in a 3 bit ADC, there are 2 to the power of 3, that is 8 possible output codes like this. Here you can see I can have 1, 2, 3, 4, 5, 6, 7, 8 codes are there, 0, 0, 0, 0, 0, 1, 0, 1, 0, all these things. Now, this is a digital representation. Okay. So, you can have 8 possible output codes. In the case of 4 bit, 2 to the power of 4, that is 16 possible codes, 0, 0, 0, 0, 0, 1, 0, 1, like that. You will have 16 possible output codes. Now, V reference, if it is okay, there are 8 possible outputs like this what I have shown. The difference between each output code is V reference by 8. See, for example, this code 00 between the voltage between the 00 code and 001 is whatever reference is there divided by 8, because n bit. So, there are 8 division, 8 such codes are there. The difference between the 2 codes is equal to V reference divided by 8, which means if V reference is 8 volts, the difference between the code 000 and 001 is 8 divided by 8, that is 1. V reference by, see, 8 volts divided by 2 to the power 8, that is 8. So, that is 1 volt. So, each number when the code goes up by one number, that would correspond to an input voltage increase of 1 volt. Now, the 00 in the ADC would correspond to analog voltage of between 0 and 1, anywhere between 0 and 1. 001 would correspond anywhere between 1 and 2. So, you can see the voltage has gone up from 0 to 1, 1 to 2, 2 to 3, 3 to 4, but between 000 and 001, okay, when the output voltage varies remains at 000, when the input voltage has varied from 0 to 1, when the input voltage has varied from 0 to 1, till that point output was 00, when the input has become 1, output has changed to 1, 001. Similarly, output remains at 001 till input voltage varies from 1 to 2, when it becomes 2, it becomes 010, the corresponding 2 volts. Okay? This will become clearer in this circuit. So, what I am showing now here is the conversion from analog voltage, a triangular voltage like this with the ADC. With time, the analog voltage is varying like this. Now, if I give this input to the analog to digital converter, okay, now you see 001, 1, 2, 3, 4, all these things would correspond to, and correspondingly the digital voltage I put. If all of them are said, 001 is 0 to 1 volt. Here you can see I am sampling this at this voltage initially, then after Ts I am sampling, I am converting that into digital signal, I am sampling here, converting into digital signal. Okay. Now, you can see at this point of time, the input is actually between 100 and 111, which means actually it is 4 volts. Okay. It is 4 and 5. So, it is between 4 and 5. If between 4 and 5, when it is between 4 and 5, the digital output will remain at 100. 100 will give between 4 and 5 out input. Okay, you have to see corresponding to this analog, what is the previous digital, that is 100. What will happen is, it will sample here, generate a digital output which is 100. You can see I put the output sequence as 100, a pulse 1, nothing, nothing. So, these 3, this showing 0, 1, 0, pulse width corresponding to that. Then after time TFS, it is sampling here. Okay. So, here what is the voltage? It is between 110 and 111, actually it is 5 volt. This will be 5 volt here. Okay. This is 110 and 110, I am sorry, 110 and 111 between that. So, 6 volts, that is 6 volts, corresponding 110, 6 volts is the one. So, 6 volts will be the digital output will be corresponding to, when the output voltage, input voltage is 6 volts, so long as input is between 6 and 7, the output will be 110. So, it is between 6 and 7, the output will be 110. So, you can see it generates 110. So, pulse width is 2, there is 2 pulses are there 110. So, like that it goes on repeating. Okay. For example, here it is between between 1 0 0 and 1 1 1 the signal, which will actually correspond to 1 1 0 1 1 0 1 1, that is 3 volts. So, it will correspond to that. So, the pulse here will generate a signal which is 0 1 1. So, like that will go on. This sequential output will be representing how much is the digital output corresponding to this here. Next will be how much is corresponding to this, that is this one. Next is how much is corresponding to this, that is 0 1 1. Next corresponding to this 0 1 0, corresponding to this, that is 0 1 0 1 1 0 1. You see 1 0 1. Okay. Now, finally, the digital signal will be converted to analog signal. What happens is, between this signal and this signal, the output remains same as this value at this value, analog output. Okay. That is, if it was 5 volts 1 0 0, if it is 4 volts, it will remain at 4. So, output voltage will be finally, when you convert the digital output to the analog output using a D to a converter, it will, the output will be like this. You are actually, whatever was digital signal input was like this, blue has become green like that, okay, because your voltage remains at this value till the next voltage comes in. So, that is the idea of that. So, if I make it sampling closer and closer, this output will be closer to this particular input signal. So, this is the idea of the analog to digital converter. You use A to D converter for signal processing, D to A converter for converting back to analog, because ultimately you need analog signal to do some work. With that, I close down today's discussion. We will go on with further on these aspects in my next lecture. Thank you.